delta positive such that if we are in the neighborhood of T naught, such that f of t is bigger than or equal to epsilon. Can we have this actually as a coordinate from the coordinate? Okay, we have this from
H of
oh sorry, h of so it must be h of So epsilon is a positive number. I can always find a delta such that if my t is in the neighborhood of t naught, then h of t is bigger than or equal to epsilon. Basically, it is another way to write this. It's nothing else. So when I am saying that h of t naught is positive, what does it mean? It means that if you are in the neighborhood of t naught, your h is always going to be bigger than or equal to epsilon, which is strictly positive. Okay? Epsilon, which is strictly positive. So it's just nothing, it's just rephrasing this statement. Okay? Now if I have this, then I have something interesting actually. Now, consider this. Consider the integral of h of t. Consider the integral of t naught minus delta, t naught plus delta h of t dt. In other words, in the neighborhood of, in this small neighborhood of t naught basically. So if I compare these both, which is going to be the bigger one? Which is going to be the bigger one?
A to B.
There is a line to be the bigger one. And I can say that this guy is bigger than or equal to 0.
यहाँ पे साइड 0 है because of our assumption.
नहीं वो तो ठीक है और 0. But what we gonna get from other side? So in this interval, I know that my h of t is bigger than or equal to epsilon. So I would say that this is bigger than or equal to epsilon times t naught minus delta n t naught plus delta n t, which is equal to epsilon delta. Okay. Now, is this something interesting? What trouble we got? Do you see the trouble? Where is the trouble?
Something positive is less than 0.
Something positive is less than 0. Why? Because if this is 0, then 0 is bigger than or equal to
It's positive.
something positive, which is a miracle. And when such miracle happens, we say that, throw away such rubbish assumptions basically. Okay, this is a contradiction. That is, that 0 is bigger than delta epsilon. Okay? Bigger than or equal. Bigger than or equal. It neither can be equal to 0, nor 0 can be bigger than 2 epsilon. So that's a contradiction. And thus we have the result. Okay? Once we have the result. And once you have this result, then we are done with the proof also that basically if the inner product FF is 0, then F must be also 0.
सर एक स्टेप में थोड़ा मसला हो रहा है वो जो हम दे रहे हैं ना पार्ट N into epsilon and delta, वो किस तरह से लिखना है?
I'm saying that I'm just rephrasing this system.
इसको लिखने में
I'm just rephrasing this system. I'm saying that h of t naught is positive and it is continuous actually. So if it is continuous, okay, so h of t is positive, okay. So what does continuity is doing roughly? Think about it. Continuity throws near points to the near points basically. Okay. So if your function is continuous and you have points in the interval a to b, okay, and you transform them through the continuous function h, they are still going to be near. Now I am saying that f of t and 0, h of t naught and 0 are roughly near to each other. So therefore, if I am saying that if I have two inputs, okay, which are near to each other, then h of t is still going to be near to what? Epsilon, which is bigger than 0. So I'm just doing nothing, I'm just rephrasing this system. Okay? Now, the definiteness of a to b follows that if I have ff to be 0, that means that the integral of the magnitude of f of t square dt is 0. Okay, if this is 0, then from this result, now just take h to be magnitude of f of t square. So magnitude of f of t square is continuous and it's non-negative and integral is 0. So therefore this magnitude must be 0. Okay? Therefore this magnitude must be 0. So if the magnitude is 0, then f of t must be 0 as well. If f of t is 0 on all points of a to b, then what we can have is that f must be 0. Okay? So lots of work. Last thing that I would like to do is to just give you a hint and you have to do it for yourself afterwards. Basically, now once we have inner product, notion of inner product, we are in position to define the geometry of the vectors basically. Okay. So in other words, if you have a vector space and you want to have a geometry of the vectors, in other words, you can talk about angles between two vectors. And those vectors are not really vectors in 3D or RD, so they are functions actually, or maybe matrices or something like that. Okay. इस वक्त फिलहाल क्या टाइम है? Definition. So if B with some inner product space, then for an element in V, I can define notion of magnitude, and this magnitude must be what? This magnitude must be equal to the square root of the inner product x and x. Okay? The square root of inner product x and x. And it makes sense actually if you just think about it. So just take an example in R3 for example. Okay, so what could be x and x in R3 if you take the inner product? So is going to be sum from I equal to 1 to 3 xi square, okay, and which is same as magnitude of xi square in R3. Agree? Yeah, norm. And therefore, I can deduce that at least in R3, this is same as the product of x and x. So it's really the generalization from finite dimensions. Okay. Next thing that you have to show is basically that this, so using the properties of inner product, you have to show that homework also, that magnitude of x is non-negative. Okay, it has its non-negativity property. And the second is all properties of norm that you know. You know that all properties of norm. What are some of basic properties of norm? So it's like a positivity and definiteness. So magnitude of x is 0 if and only if x is 0. And then, you know, what do you call, if I have a lambda, which is a scalar actually, and multiplied by x, it must be same as
lambda square.
Absolute of lambda times the magnitude of x. Okay? And the fourth property is that if you have x plus y, magnitude it must be less than or equal to magnitude of x plus magnitude of y, which we call the triangle inequality. Okay? Alright? So you have to prove these, drive these identities, okay, by using this definition. Okay, you need to keep this thing in head that this inner product xx is an inner product basically. So it has all these properties, all the properties of inner product. And you have to use those inner product properties of inner product and try to prove basically fundamental identities, okay? Fundamental properties. Now this norm that you get basically on vector space.
Can we say that this is a norm from inner products?
Yes, this is what that I'm going to write actually. That this norm that you have got basically now, this norm we're going to call, it's called, what do you call, induced norm. Yeah, norm induced by norm induced by the inner product. Okay. Call this space as induced normed space actually. Okay, we're going to consider the normed spaces in the next chapter. The next chapter is all about normed spaces. But that would be an independent topic, but at the moment we have kind of deduced norm from okay. So let's take two examples of norm. So what would be the norm on KD? So what you can have norm of x basically, where x is an element in KD, so it must be by definition equal to what? The square root of inner product x and x, and And what is the square root of inner product x and x? So it's going to be the sum I equal to 1 to d xi times xi, so complex numbers, and it must be same as sum I equal to 1 to d and magnitude of xi, this magnitude of xi square. So this is what you call the norm on KD. Okay? The norm on KD. And if you see, this is same as the norm of x in the space KD. Okay. See that this is what the definition is. Okay. How about the norm on CAV? What would be the norm on CAV? What would be the norm of F? So you see, here's a pretty interesting thing now. That okay, it was pretty trivial to give the notion of norm actually on KD, but it's completely non-trivial to have a meaning of size of a function basically, or a magnitude of a function. Just think about it. Okay? So you can have a magnitude of a number or maybe a complex number, but what would be the meaning of magnitude of a function actually? That is pretty interesting. Why? Because, and why you get that from the structure of the inner product space. And the inner product is allowing you to compute the magnitude. It's something that it's like you have a vector space and you want to talk about magnitude, try to define an inner product. Okay. This will allow you to have the notion of what you call length. So in other words, we are saying what is the length of a function. So we can have a length of a number, but what's the meaning of length of a function actually? So it must be same as ff. So it should be equal to what? It should be equal to integral from a to b, ultimately magnitude of ft square dt. This must be the norm induced by. Okay? And the last thing, which is also going to be the homework for you. Okay? Lots of work to do. We're going to cover lots of the stuff. It's pretty easy, not difficult. I'll just show you how to do one property and then you can do the rest. So here are some geometric properties of norms. So in other words, if we have defined norm, now we can talk about some of the properties. Yes?
dt square?
Huh?
dt
No, it shouldn't be dt square. Obviously. There are some properties of norms. Properties of norms. Not only properties, but actually these are what you call the geometric properties. Okay? So now you talk about the geometry. So there's a lemma. Okay. It says that okay, if I have V and an inner product on V, so vector space with an inner product on it, V and inner product space. Okay, it's also called a pre-Hilbert space. Sometimes you will also have this pre-Hilbert space. So why you call it pre? There's a reason for it. Right? So once you will know that what's a Hilbert space actually. So therefore, it will be a pre-Hilbert space. Then following is true. It's true for all f and g in V definition. F and g are abstract notions, they are not functions here. You have to keep this in mind. Okay? You can have x and y definition. So here is what do you call the first plus G square norm is same as magnitude of F square plus 2 times of Fg plus magnitude of G square. Have you seen something like this before in your entire life? Have you seen it? What is it? बचपन से देखते हैं a plus b का square. A square plus b square plus 2ab something like similar. So have a try to guess what would be f plus g square and minus f minus g square. Keeping in view this.
4 never nine.
So it should be
4 times.
So it is going to be 4 times
Never nine.
fg in the product, but the real part of the product. A bit different. This is called polarization identity. Okay? Polarization identity. When you are young and proving that identity a plus b square and a minus b square, you are basically proving a version of polarization identity. Okay? And how about this third one? Have a guess. So what if I have f plus g square and plus f minus g square, so it should be equal to what? Yes.
2 times log of f square plus log of
2 times of norm of f square plus
log of
g square actually. This is called parallelogram law. So just tell me which of identity I must prove, and then your task is to do the rest of it. Let me do the easy one. Okay. Let me do the first one. You must have fun with it. So what would be f plus g square magnitude by definition?
In the front of a plus g command.
Exactly. So it must be. So see, it's just a simple algebra. F plus g, f plus g. What would be this?
The linearization.
This would be
A comma A plus B.
ff plus fg
G
plus gf plus gg. Okay? So you're almost there. So it's going to be magnitude of f squared, magnitude of g squared, and what should I do with these two basically numbers? What do you think?
one is equal to
G is equal to
No, it's not equal basically.
conjugate.
So it's fg plus if I exploit symmetry, so it's going to be
G.
fg conjugate. Fg conjugate. Okay? And what you get when you add a number to its conjugate. Just think about it. So you have x plus iota y and x minus iota y.
real part of that.
So you get the 2 times of the real part. So this plus 2 times of the real parts of it. Enjoy yourself.
But you can write this in identity.
Huh?
What's the identity of identity?
Yeah, the literal.
Yeah? Ah, okay. So you must have done the real part here. Okay? So have fun with these. See you tomorrow. Okay? So you have to work hard, beta. There's lots of things that we need to cover. These are things, and I'll be pretty quick on this first stuff because that I know you have done some parts of product spaces. So what we covered is basically 2 sections, 1.1 and 1.2 of this first chapter of 1.1 actually of the first chapter. And what we are going to do tomorrow is to finish up this chapter, basically, which is 1.4 and 1.2 and 1.2. That's it, okay? And your task is to, so let me tell you another thing finally, that your task is to, so you will find 3 kind of exercises actually in exercise book. Okay, 3 kind of exercises. So you will, at the end of each chapter, you will find some exercises with index A actually. So 1A, 2A, 3A, 4A. So these are easy exercises. Easy in inverted commas. Okay? These are easy exercises. So I expect that at least we all should do basically these easy exercises. Okay, which kind of directly follows from what you have learned actually in the text. Then you have exercise of type B, okay, which is a bit more sophisticated. Okay, they can follow from text and some more information actually. Okay, and then you can also find some C category exercises, which are really the expert level exercises. Some good level. But for that you have to basically think very cleverly to do exercises. So what I am expecting is that we must all, at least do all A exercises, A type exercises, and from B type exercises I'll tell you specific exercises to do. Okay? But some of you guys must attempt C type exercises as well. But at least from the point of view of exam and all that, they will be important. Okay?
Yes, sir.
See you tomorrow. कल किस वक्त है क्लास? 12 बजे।